All right, hey guys, how's it going? We're going to continue on with our derivatives over here. So this is going to be the last thing that's going to be on your quote-unquote chapter test. I'll be giving you guys a little bit more information on that this upcoming weekend, but let's just jump right in. So really quickly, this week we're going to be talking about derivatives and a little bit more on implicit differentiation, and we're just expanding upon our implicit differentiation basically. So we're going to be talking about higher order implicit differentiation. That's like second and third derivatives of implicit differentiation of inverse functions. I'm going to kind of skim through this specifically to talk about differentiation of natural log, and finally we're going to end up with differentiation of inverse trig functions. So that's kind of what we're going to be working on today. So let's dive on in. First off, when we're doing differentiation of higher order implicit differentiation, basically how do we find the rate of change for a function based on two variables? So let's kind of go over an example on that really quickly. So if I'm doing something like this, let's just do our differentiation as we normally would. So I'm going to take dx over both sides, and then from there, I want to find dy dx. So we're going to take the derivative with respect to x on both sides. So I'm going to get 2y dy dx plus 2x equals 0. So then from here, I'm going to get dy dx equals negative 2x over 2y, which means that my derivative of y with respect to x is equal to negative x over y. Now I noticed on Discord a handful of you guys were saying you still wanted extra practice with this, you needed help on this. So if you still need help on this, make sure you guys let me know, and then I can jump on Discord to help you. I don't want to limit you guys to only rider time, so make sure that you guys are saying, hey, Mr. Marmoto, I need help, can you just jump on real quick? Or if you want to come to rider time, you definitely can. Just ask me on the Discord. I do have a rider time link that I use for my Geom Honors kids as well as my Alg 1 kids, and I can make one for you guys as well if that would be helpful. All right, so now let's talk about the second derivative. Basically, all we're doing with the second derivative is now we're taking the derivative of my derivative function. So this is kind of what it looks like. We're taking the derivative of both sides. So that way we're going to get our d squared y over dx squared equals the derivative of this over here. And basically, we just take it exactly how we would assume we would take it. So let's kind of go over this. What we're going to do is we're just going to say d squared y over dx squared equals, and then now this is a quotient function, so we have to have our quotient rule. That's why our rules are so important. We just use the same thing over and over. So all I'm going to go is low d high minus high d low. So this is low, oh, excuse me, let me put the negative in front so I don't need to deal with that. So it's low d high minus high d low. And the derivative of my lower function is dy dx all over low, which is y squared. Now, once I'm here, we know what dy dx is. Based on our previous function, we found out that dy dx was equal to negative x over y. So we can just use that. And again, that's the beautiful thing about math. Once you have something that's defined, you can use it over and over, which is why we have to watch out for our notation, because it's really powerful. So we have our d2y over dx squared equals negative y plus x squared over y all over y squared. And then from here, we can just kind of simplify. So then I'm just going to get d2y over dx2 equals negative y squared over y plus, oh, let me just do a couple steps, plus x squared all over y squared, which means my final answer is going to be d squared y over dx2 equals negative y squared plus x squared all over y to the third. And that's it. And that's our second derivative function. So let me kind of make this a little bit nicer. Basically, this is what's going on. Again, all we're doing is we're saying if I'm taking the derivative, we're doing our low d high minus high d low, and we're using the fact that we know what dy over dx is, and we know that that's negative x over y. And then from there, we just simplify. Now, just as a quick reminder, the interpretation makes a difference. So the first one is saying, hey, let's take our derivative with respect to y. So what is the slope of my tangent line going to be on this function given an x and a y? What the second derivative is saying is, okay, how is that slope changing as my x and y change? So it's the rate of change of your rate of change. Again, when we're doing higher order derivatives, it's not the interpretation that matters so much, because again, it always is like, okay, what's the rate of change versus the rate of change of the rate of change? But the mechanical way we're going to do it is we're always going to remember, hey, let's use our dy dx when we're taking our second derivative. None of our rules have changed whatsoever. We're still using product rule, we're still using chain rule, we're still using quotient rule. All of those rules are the same, and implicit differentiation still holds too, that whenever I'm taking the derivative of something that's not the variable in my denominator, we always have to make sure that we're adding on that tax, that dy dx kind of thing, and all of that stays the same. It's just when we're using higher order derivatives, if I have a dy dx like I did back here, we can always just replace it with whatever we found our first derivative is. So again, it's really nothing very difficult. It's just a matter of, okay, let's kind of think outside the box a little bit here, or let's just be open-minded. Okay, next, we're going to talk about inverse functions. When we're doing the derivatives of inverse functions, basically the idea, the main goal here is we're just trying to figure out how do we find the derivative of the inverse function. There's a really long proof, and it's a really short equation, and it's really not used really often. So for as of right now, I don't think it's worth showing you the derivation, but I think it is worth sort of kind of knowing what it is. So you do need to memorize this. The derivative of an inverse function is going to be 1 over the derivative of the original function of the inverted function. And let me kind of explain what that means. So the best way to do it is kind of with an example. So with this in mind, let's look at our x cubed function. The inverse of this is x to the 1/3, or our cube root function. Now, if we're taking the derivative of our inverse function, we're taking the derivative of our x to the 1/3 function. So we're saying, okay, let's look at this. How do we take the derivative of this? And if I gave you this problem, you should be able to figure out it's this purely using your power rule. It's really, really simple, but we're going to show you how this function works. Okay, so let's kind of go through it. So in order to take the derivative of my inverse function, we go 1 over the derivative of our original function. So the derivative of our original function, f prime in this case, is going to be 3x squared. Oh, excuse me, f prime is equal to 3x squared. Okay, this is what our derivative is. So when we plug in f invert of that, we get this. Again, we're still just working off of this big function here. It says in order to take the derivative of my inverse function, we go 1 over the derivative of the inverted function. So it's 1 over 3x, so we're plugging in f inverted of x into there. And what we know is f inverted of x is x to the 1/3. So we get 1 over 3 f inverted of x, or x to the 1/3 squared, and then we're going to end up with 1 over 3 x to the 2 over 3, or basically another way to write that is our 1/3 x to the negative 2 over 3. And again, like I said, in this case, it's really easy. It's not worth using this equation because we're able to use power rule in order to find the derivative of this x to the 1/3 function. But that's kind of how this inverse derivation formula is working. It says use the original function, take the derivative of that, and then plug in your inverted function. So let me show you a less easy example. And this is kind of why it's useful. If I asked you to find the derivative of ln x, find the derivative of ln x, it would be really hard because it doesn't follow any of our rules. We don't know how to use product rule for this. We don't know how to use power rule. So instead, what we're going to do is the inverse of ln x is e to the x. And we do know how to find the derivative of that. That's really easy. So instead of calling f of x equals ln x, let's think of it like h of x is equal to e to the x, and h inverted of x is equal to ln x. So now we can find the derivative of our inverse function. The derivative of our inverse function is just going to be 1 over the derivative of our original function of our inverted function. So let's kind of look at that. The derivative h prime of x, in this case, is going to be e to the x, because this is our indestructible function. Whenever we take the derivative of e to the x, it's still e to the x. So we're going to go 1 over e to the, our inverted function. So we're going to get 1 over e to the ln x. And e to the ln x is just x, which means that the derivative of h inverted of x is 1 over x. And this is really nice because this tells us, hey, if I have f of x, if I have f of x equals ln x, we know f prime of x equals 1 over x. Again, what we're doing is we're saying if my function is hard to find the derivative of, but my inverse function is easy to find the derivative of, we can use this inverse function derivation rule in order to kind of work backwards. It's kind of convoluted. And again, that's why I don't want to spend too much time with it. But basically, whenever you're taking the derivative of inverse functions, we're going to be using this formula here. And for me, when I'm giving you special rules, if I'm using it, it'll just be something we keep in the back of our mind. For now, this is the important thing. Whenever I'm taking the derivative of an ln function, or the derivative of my natural log, it's just going to be 1 over x. That's it. And the way we found this was using our inverse derivation rule. Okay. Again, like I said, the main thing with our derivative of our inverse is just a tool that we can use in our back pocket. It doesn't pop up too much on the AP exam as a question in and of itself. It is good to have, especially if you guys are going to be doing multiple choice, which we don't know if that's going to be the case this year, but it is nice to use. At the very, very least, though, it is going to be something we're going to be using for specific derivations because, again, with our rules, we don't have any rules for finding ln x, but we do know how to find e to the x. So since we know how to find the inverse function, let's take the derivative of the inverse and apply that to this function. Basically, again, it's more of a deriving tool for new rules rather than it is something you're going to be commonly using. So this one here, important to memorize. This one here, good to have in your back pocket, but not necessarily memorized. So again, when we're taking the derivative of natural logs, the derivative of a natural log is just 1 over x. And this is a function. This is a natural log function. So we treat it like a function, which means chain rule and all those fun rules apply. So we treat it kind of like we would sine or cosine. So basically what we're going to do is we're going to say, let's look at the outer layer first when we do chain rules. So we're going to take 1 over whatever this is, x squared plus 1. And then all we do is we multiply that by 2x plus 0. So the derivative of this function here is just going to be 2x over x squared plus 1. That's it. Again, when we're doing derivatives of our natural log, it's just a simple chain rule. And the derivative of the natural log is 1 over x. That's a new rule that we can use since we derived it using our inverse function derivation rule. Okay, moving on. The next thing we're going to do is we're going to work with inverse trig derivatives. Now, if I give you y equals sine inverse of x, if I want to find the derivative of this, dy dx, again, we don't have any rules that tell us how to deal with this. We can't use power rule because this -1 isn't a power. It's very specifically not a power. It's very much so a, it's an inverse. And that's why context really matters, because if we had like sine 2, then yeah, that's a squared. But this -1 is telling me that we're using an inverse. So you got to be careful of that. So we don't have any rules how to deal with this. So what we're going to do is we're going to use our inverse derivative of our inverse, because we know how to find the derivative of sine, and we're going to play with that really quickly. But before we do, we're going to draw this out. Let's think about this triangle here. Whenever we're working with inverse trig, we almost always drew this triangle because y equals sine inverse of x is really saying, what is the angle going to be if I give you the ratio x? Right? Remember, what sine, cosine, and tangent say is give me an angle and I'll tell you what the ratio of the sides are going to be. When we're doing the inverse, we're saying give me a ratio and I'll tell you the angle that pops that out. So when we're saying y equals sine inverse of x, really what we're saying is I have some angle y in a right triangle. Yikes, this should be a right triangle. Hello. We have some angle y in a right triangle, and my opposite is x, my hypotenuse is 1, which means my adjacent side using Pythagorean theorem is square root 1 minus x squared. So this is a really common thing we did when we were solving inverse trig triangles. If you forget how to do that, feel free to ask me, or you can just look that up and just do a quick brush up. But this is kind of what this is saying. Now, with this in mind, we can use this. Now, if my f, to find the derivative of my inverse, let's just call my f of x equal to sine of x. So that way, it'll be easy for me to find the derivative of my inverse when we use this function here. So let's play with this a little bit. So here's what's going to be happening. I'm going to call my f of x sine x. So my f inverse of x is going to be sine inverse of x. So then now from here, basically what we're going to do is we're going to replace our f prime of x with cosine of x because my f of x is sine. So if my f of x is sine, that means f prime of x equals cosine x. And then so using that, if I plug that into here, we can put cosine of sine inverse of x. But again, what sine inverse of x is saying is what is the angle that gives us a ratio of x. And the angle that gives us a ratio of x, in this case, is going to be y. So that's why I replaced it with y over here. You don't need to know this too well. This is just a derivation. I'm going to give you the formula. Once you know the formula, you can memorize that. But this is kind of how it's working. Now, once we're here, cosine of y says, what is my adjacent to hypotenuse ratio? So we're going to take adjacent over hypotenuse, and then we're just going to get square root cosine of y equals square root of 1 minus x squared over 1, or just 1 minus x squared. So when I plug that in for here, we're going to get this. So again, using this inverse derivative of my inverse formula, what we found out is that the derivative of sine inverse is simply going to be 1 over square root 1 minus x squared. Again, this is built on the fact that you guys are pretty doggone good about using your inverse trig functions in order to solve triangles and whatnot. Again, sorry, I should have had a right angle over here, but hopefully you'll forgive that. And this is your main takeaway. So using that, let's look at our other trig functions. Now, I'm not going to show you how to find cosine and tangent because you're basically doing exactly the same thing. We're saying, okay, let's call h of x equal to cosine x. So then now, to find h inverse of x, we're just going to use that derivative function, 1 over h prime of h inverse of x. But basically, this is the important thing that you guys need to know. You need to have these memorized off the top of your head. Now, some people write this one like this, but another common one, if you guys are using extra resources, is 1 over negative square root 1 minus x squared. But again, as you guys should know by now, that's literally the same thing. But it's just dealer's choice how you want to deal with it. Okay. So let's kind of play around with this now. So let's find the derivative. Let's find dy dx of y equals 7 tan inverse of 4x cubed. So then now all we're going to do is we're going to say dy dx equals 7 times by, and this is chain rule because I have a function 4x cubed inside of my function. So we deal with the outer function first. And my outer function, what we know is tan inverse of x is 1 over 1 plus x squared. So we're going to get 1 over 1 plus blank squared. And the thing that goes inside of my blank is whatever was originally inside of your function. So this is going to be 4x cubed. So that's my outside function. Now, according to chain rule, we have to take the derivative of my inside part. And the derivative of my inside part is 12x squared. So dy dx is equal to 84. What is that? 84? 84x squared all over 1 plus 16, x to the 5th, or x to the 6th, excuse me. That's it. Again, we're just using chain rule. And it's a little weird because we started with the tangent and we ended without any trig functions. But the reason why we did that is, again, this is how we find the derivatives of our inverse trig. And the way we got these equations was by using this little triangle here, as well as this little inverse trig, or our derivative of our inverse function formula over here. Like I said, this formula is normally used for finding new rules, like our natural log and our inverse trig derivatives, but it is nice to have in the back of your pocket. All right, let's move on with our lives. So in summary, when we're doing implicit differentiation of higher order derivatives, there's a key. You're going to need to keep doing your rule. So whenever I'm taking the derivative of something that's not in my denominator here, we have to include this little tax. Now, when I'm doing the second derivative, I'm going to end up with a dy dx inside of my answer. The way we get around this is we know what dy dx was based on our first implicit differentiation. We just plug that in. Next, you can use derivatives of inverse functions to find the derivatives of functions that don't conform to our normal rules. So we can say, hey, if I don't know how to find the derivative of this function, but the inverse function is easy to find the derivative of, then we can use this rule over here. Again, it's not super important that you know this. It's more of a tool that we use as math teachers and mathematicians in order to find new rules, rather than AP Calc students who are trying to mechanically do this a lot more. But anyway, so the derivatives that we got based on this over here as our tool is, we know now that the derivative of a natural log is 1 over x. And the derivative of our sine inverse is 1 over square root 1 minus x squared. The derivative of our cosine inverse function is 1 over square root 1 minus x squared. And our derivative of our tangent inverse function is 1 over 1 plus x squared. All right, that's it. If you guys have any questions, let me know. You guys have your homework packet up already. Again, take advantage of writer time. I know I haven't been giving you guys the most attention because honestly, my Algebra 1 and my Geom honors really have been requiring a lot of attention lately. So I apologize for that. But again, as seniors, I know that you guys know what you need in order to study. I've been working with you guys a lot more, so I know you guys can tell when you know it and when you don't. Even if I'm not posting anything necessarily, if I'm not necessarily posting a writer time, just take advantage of the fact that I have ways for you to communicate with me. And I've been trying to build that culture where it's easy to communicate with me. So feel free to ask me questions at any time, even outside of writer time. My door is always open, I guess, for lack of a better word. But again, thank you guys for hanging in there. If you guys have any questions, let me know. Again, the goal of these videos is just trying to keep it a little bit shorter and just go over the main ideas. Okay, see you guys later.